Okay, here's a DSP video on system classification. Specifically, we're going to look at linearity. Okay, so in class last week we talked about this a little bit, but I wanted to clarify this and sort of start from the beginning and do a few examples to help you understand this concept. Okay, so in class we had talked about the definition of linearity. All right, so this diagram illustrates it really well. The idea here is that this has to work for all. All right, so for all x1 and x2, any choices that we happen to make, and for all a and b, if I apply system 1 here, okay, so the top part is system 1, I take x1, multiply by a, x2, multiply by b, add those together, put it into the system, I would get a certain output y1, okay? If I do that in a different order, if I take x1 on system 2 and apply that to the system, multiply by a, take x2, apply that to the system, multiply by b, combine those together with a sum and get a second output, the system is linear if and only if y1 of n is equal to y2 of n. Okay, so that's what we talked about. In class, we talked about a specific example of a system where we take x of n and we apply it, plug that into the system, and in this particular case, the system was squaring. All right, and in class, we'd show that was not linear. Okay, so I wanted to do a few examples of that just to illustrate the point a little bit more. Okay, so let's say, for example, we chose this particular system, the squaring system, and we wanted to investigate this. Let's pretend like we don't know it's nonlinear. All right, and we wanted to investigate this, and we said, all right, let's let x1 be an impulse. All right, and let's let x2 of n be another impulse. All right, let's make a equal 1 and b equal 1. All right, if the system is linear, if we apply these two situations, this particular choice of inputs in a and b to the two different systems, we should get y1 is equal to y2 if the system's linear. All right, so we can go through this pretty quickly. If I plugged in, let's change the pin color, delta n here. If I scale that by a is equal to 1. I would get delta of n here. If x2 is delta of n, b is equal to 1 also, this would be delta of n. When I sum this, this would be 2 delta of n, and when I apply that to the system says to square it. What I would get out is 4 delta of n. Okay? So, that seemed to work. All right? I say it seems to work. We haven't even done the second system. All right, so the next thing to do is to plug in the same exact parameters. Okay, so we have delta of n here, delta of n here. When we square it, 1 squared is 1, so this would be delta of n coming out. Then we scale this by 1, so we'd have delta of n plus delta of n, and that would be 2 delta of n. All right, so by just randomly choosing a couple of inputs, we can see that y1 of n is not equal to y2 of n, and therefore, this is clearly proven to be not linear. Okay, let's now consider the same system, which I admit we already know is nonlinear. But I wanted to show you that it's possible to guess wrong. If you're just guessing signals, you could guess something that would seem to indicate that the system is linear. Okay, so let's take the example where we have x1 of n is a unit step, and x2 of n is also a unit step. Let's make a equal 1 and b equal 0. Okay, so this is a perfectly valid choice of signals to do a test case on. We have to have linearity condition being true for all possible combinations of input signals and parameters a and b. But, we can test it and see what happens. All right. So if I put in x1 as a unit step, this would be a unit step here. A is equal to 1, and so coming out of there would be a unit step. X of 2 is also a unit step, but this time B is 0. So we have 0 coming into the summer, and coming to the input of the system is a single unit step. Okay, the unit step is 1 for positive n, so if we square 1, we also get 1, and so the output here would be simply a unit step function. Okay, so let's apply that to the second block diagram. All right, so again, if x1 is a unit step, we square that, square a unit step, you get a unit step. A is equal to 1, so I get a unit step here, and on the lower half, unit step, square this, out comes a unit step. B is equal to 0, so 0 times anything is 0, and our answer is a unit step. All right, so I did this example to show you that for this particular case, y1 of n is equal to y2 of n, which seems to suggest the system is linear, but we know this has to be true for all x1 and all x2, and so I'm trying to make the point that if you just plug something in and you guess badly, you don't know whether it's linear or not. Okay, in this particular case, we know it's not linear, even though it's satisfied for this one particular case. Okay, for this next example, I wanted to show you what happens when a system is linear. All right, so I've done enough of these to know that this is a linear system, and I wanted to be able to show you how you prove that it's linear. All right, my goal for you is to get to the same spot where you can just look at a system and know whether or not it's linear. All right, so here we go. Our system definition is you take whatever the input is, this would be x of n, and you form the new system, or the new signal, which is a scaling by 2 and a time shift by 3. Okay? So, to prove something's linear, we have to apply both of these systems, find y1 and y2. All right? So, looking at the upper path, and again changing this to red, if I put in any signal x1 of n, so I'm representing that as a general signal, just x1 of n, and I multiply that by a, what I have coming into the summer is ax of n, x1 of n. Same thing with this lower half, b x2 of n, and I sum these two signals together and put it into the system. And what does that tell me to do? Well, I have into the dot here, I have a x1 of n plus b x2 of n. All right, so moving this down, the transformation says to multiply this whole thing by 2, and everywhere I see an n, I delay it by n minus 3. Okay, and so that's my output y1 of n. Okay, so let's now consider y2 of n. All right, so we take the same approach. We put in x1 of n, we put in x2 of n. This time we do the transformation. The transformation says multiply by 2 and delay by 3. All right, then we multiply by a and b and we add those together. So y2 of n is 2 x1 of n minus 3 multiplied by a. All right, so let me move that over. Plus b times 2 x2 of n minus 3. All right, and so then the question is y1 of n equal to y2 of n? And what I do from there is I do valid mathematical operations to try to prove that these two things are equal. And so what I know is that multiplication distributes, okay, and that multiplication is commutative. And so I can do the algebra and show that that 2 goes through, and these two expressions are in fact identical. All right. So when I was a student, it felt like I wasn't doing anything, but if you're careful with this, you realize that what you're doing is you're applying things in different orders. And if it's linear, the order doesn't matter. That's why it doesn't feel like you're doing anything. Okay, so hopefully this gives you a better sense of what kinds of systems are linear. We're going to be talking through several more examples as we go. So, take this and kind of build on it.